All right, good morning, chemists. We'll get started. Hopefully everyone had a great weekend. Such nice weather, almost fall time. Actually, no, I had my first pumpkin spice latte last week, so it is officially fall. So last week we left off talking about types of reactions. This is chapter 3. This is the last chapter that's on midterm 1. I called this the meat and potatoes of chemistry. So we'll finish up with types of reactions and then get into a lot of calculations today. So calculators out would be a great idea. Okay, so we will discuss 3 types of reactions in this chapter. And so we can identify what kind of reaction we're working with depending on the substances that are present on the products and the reactant side. So the 3 types that I have here: combination, decomposition, and our favorite, combustion reactions. And I have in the corner, you know, what's the kind of the defining feature for these different combination or these different types of reactions. So we did some examples of balancing stuff. And so my strategy for all of these, turning words into equations type thing, we want to identify the identity of our substances we're working with. So again, naming comes back into play. Us understanding the different phases, the different ways that elements exist on our planet. So when I talk about oxygen gas, I don't mean O atom, I mean O2, because oxygen is one of the 7 diatomic molecules, diatomic elements that exist as a diatomic on our planet. So here's an example. We take aluminum metal and then chlorine gas. Both of those are elements, but aluminum is just, you write it with a single atom, and then chlorine gas is one of our diatomics. So we identify the identity and the formulas for the substances we're working with. We use appropriate subscripts. So subscripts are tied to identity, and then we balance the reaction using coefficients to make sure that the atoms balance. So we did a combination reaction, then a decomposition reaction with some other elements here, and then I think we left off with our combustion reaction example. And so in this question, I'm proposing, okay, gaseous propane, so it's a gas, undergoes complete combustion. So we know combustion means to react with oxygen to make CO2 and water. But the idea here is I didn't give you the formula of propane. We definitely need that to balance it. So we need to get that formula from the structure. Because I told you don't memorize the full formulas for all of those alkane prefixes, so like methane, ethane, propane, etc. Don't memorize, that propane is C3H8. Just draw it. Understand that carbon always has 4 bonds, and you can always get it on the fly. So we did that here, where we understand that prop means how many carbons in a row? 3, yeah. And so we can get the full formula by understanding, okay, I need 3 carbons in a row. 3 carbons in a row. And each carbon needs 4 bonds. So the leftmost carbon will have 3 hydrogens on it. So each green line's a hydrogen. I just don't feel like writing H. The middle carbon has how many hydrogens attached to it? 2, yep, to make it 4. And then the last one on the right has 3. So we see that the formula of propane is C3H8. And we can do this for any hydrocarbon. If I give you the skeleton of a carbon-containing compound, as long as you follow the rule that carbon always has 4 bonds to it, you can figure out how many hydrogens need to be there. All right. So that's the identity of my reactant that I'm working with. So, I drew the structure. Now I have the formula, and so let's burn it now. So recognize that propane, C3H8, we're reacting it with oxygen to combust it, and then those are our products. So I'll just quickly put in those states of matter. The question says that propane's a gas. We know oxygen is a gas. CO2 also a gas, and water here is a gas because the question says to form gaseous products. Water does exist as a liquid too, but in this particular question it says, okay, you're making steam because this reaction's really hot. Okay, so there's our skeleton equation. I identified the identity of our reactants and products. Now it's time to balance it using coefficients now. So in the corner, I have here the strategy for balancing any combustion reaction. So the reasoning, you do it in this order. So you basically balance carbons, hydrogens, then oxygens. Because if we leave oxygen for last, when we balance it, then we don't like screw up all of the other coefficients. If we leave oxygen for last, to balance last, then you'll be done. You don't like mess up those coefficients that you spent so much time figuring out. Right, so I have my strategy there in the corner. If you follow the strategy, you'll be right every single time for a combustion reaction. So first we want to balance carbons using CO2. All right, so changing the coefficient in front of CO2. So let's go ahead and do that. How many CO2 molecules are going to be formed here? 3. Yep, because we have 3 carbons here in propane. All right, so then we balance hydrogens next using water. Recognize that water has 2 H2Os, or sorry, 2 hydrogens per every 1 H2. So what's the total amount of hydrogens on this reactant side right now? 8, yeah, because there's no coefficient, so there's an implied 1 there. So then how many water molecules should I form? 8? No, 4 here. We want 4 water molecules because there's 2 hydrogens per every water, all right? And so now this is the hard part. We left oxygen for last. So what I like to do is just take inventory of all of my oxygen atoms on the product side. So I just count them up. How many oxygens are coming from CO2? There's 6 oxygens, so I'll write that. Okay, so the number of oxygens, there's 6 coming from CO2, and then how many from water? 4. Yep, so there's a total of 10 oxygens that I need to balance. So I need to make sure that since there's 10 oxygens on the product side, I need 10 oxygens also on the reactant side. But here's another example where, you know, each oxygen molecule gives 2 oxygen atoms. So what's the coefficient we need here? 5, yes. And then that's it. Now we're balanced. All right, so there's an implied 1 coefficient in front of propane. We need 5 oxygen atoms, 3 CO2s, and 4 waters. And then you can take inventory of all of your atoms again to triple check that everything's balanced. So follow the strategy here in the corner. There's a little caveat here. Sometimes when we balance oxygen, there's a fraction, but don't worry. If you have a fraction in front of your oxygen coefficient, we just multiply 2 all the way across to get rid of that fraction. I think there's another example coming up. So this type of question is kind of difficult to ask on an exam. We can't have you write out a full equation. So oftentimes how we assess questions like this is we'll ask you to balance it, sum up all of the coefficients of all of the reactants and products and submit that number. Because if you screwed up somewhere and have a wrong coefficient, you'll be wrong anyway. So for this question, if we asked you, okay, what's the sum of the coefficients in the complete combustion of propane, we would do 1 plus 5, so what is that? 6 plus 7, so is that 13? 13? Yeah, so you would report 13 on to make it like an exam type question. Because it's hard to ask questions like this on a multiple choice exam. Oh, look, okay, like right here. What is the sum of the coefficients in the balanced equation for methanol? So it's another one, all right? So this could be like a numerical input question where we just ask you to report a number. But I don't give you that much information like the full chemical equation for, or formula for methanol, but we can figure it out. All right, so same strategy here. What's the structure of methanol? Let's get the formula and then let's burn it. So meth means what? 1 carbon, yes. Methanol, what does the all mean? That's an alcohol, yeah. So my strategy here is, okay, let's draw methane first. All right, so methane has 4 bonds to it. All of those are hydrogens, but to make it an alcohol, what do? Add an OH, we swap one of the hydrogens for an OH. We don't just like add an additional OH, just I'm gonna be really specific. We don't wanna do that. We just wanna replace one of those hydrogens with an OH group instead, so it looks like that, and I'll just complete it here, all right? All right, and so there's the structure of methanol, where that one of the hydrogens is replaced with an OH group, and so we can get that full formula I don't have to, I just need to write what atoms are present. So we have a carbon. How many hydrogens are there total? 4. Actually, I will write it this way. This is typically, when you see methanol written, it's written this way to show you, oh, look, there's an OH group tacked on there. It's trying to show you the structure a little bit. But even if you wrote CH4O, you can still balance it. You'll still get the right balancing. But I'm just going to write it this way because this is typically what methanol looks like. So since we're just getting the sum of the coefficients, I'm not going to bother with the states. Methanol's a liquid, but whatever. Okay, so there's the formula, so let's burn it. So we add oxygen, and our products are still CO2 and water. All right, okay, so there's my skeleton equation. So we follow the same strategy as up here, okay? So if we want to condense that strategy, basically it's balance carbons, hydrogens, then oxygens last. That's if you want to, memorize that. So let's do that. Balance those carbon atoms. So what's the coefficient in front of CO2? 1, yep, because there's just one carbon atom. And this is where it gets a little bit tricky. So next atom is hydrogen, all right? So we want to balance those hydrogen atoms, but note how this is written. How many total hydrogens are in this molecule? 4, yeah. So what is the coefficient in front of water? 2, perfect. All right, so we did carbon, hydrogen, now it's oxygen. So what I do is I take inventory of everything, all right? How many oxygen atoms do I have total on my product side? 2 plus 2, so 4, great. So I have 4 oxygen atoms that I need to balance. So I need to make sure that there's a total of 4 oxygens on my reactant side. But I have a problem. Do you see the little problem that we have? There's 2 sources of oxygen. So you might be sitting there thinking, oh, I just put a 2 right there in front of oxygen. I have 4 oxygens. What's the problem there if I do that? There's actually a total of 5 now on the reactant side because there's an oxygen atom coming from methanol. But don't worry about it, all right? We still want to have 4 oxygen atoms on that reactant side, but we're going to achieve that by only changing the coefficient in front of the oxygen molecule. So how I like to think of it is, okay, there is 1 oxygen coming from methanol. So how many oxygens need to come from the O2 molecule? 3, yep. All right, so I need to make sure that there are 3 oxygens coming from the O2 molecule. So what coefficient do I need in front of it? It's not 1, it's not 2, it's 1.5. Yeah, so it's actually 3 halves. Right, so I need a coefficient of 3 halves in front of that oxygen, all right, because each oxygen gives 2 oxygen atoms, so 3 halves times 2 equals 3. So that's how I get 3 oxygen molecules, yeah, or atoms. You can put 1.5, but I'm actually not done yet. I'm not done yet. So the reason I put 3 over 2 is because we can't have a fraction in our coefficients. So what I'm going to do to get rid of it, this is the very last step of my strategy, but this is only if O2 has a fractional coefficient, so like 3 halves or 1.5. We just want to multiply 2 across every single coefficient to get rid of it. All right, so like right now I have a coefficient of 1 in front of methanol, 3 halves in front of O2, 1 and 2. So I'm just going to take all of those coefficients and multiply by 2. And so what are the new coefficients now? What's the new coefficient in front of methanol? 2. And then what's the new coefficient in front of O2? 3. Yeah, I left it as 3 halves because then you see, oh, the 2's cancel, you're left with 3. That's why I do it. Then we have 2 CO2s and 4 waters. And so we see when we add all of that up, oh wait, my answer in the corner is wrong. Is it? Yeah, it's wrong, sorry. Is it 13? I guess it's 13. Yeah? What? What's going on? 11's right? I added wrong right now. Okay, 4, hold on. No, okay, I'm right. Yes, so 2 plus is 5. So, yes, okay, 11 is right. Okay, perfect. All right, so yeah, and so then we would port an answer of 11. And so the reason I left it as a fraction, let's pretend we wanted 8 oxygen atoms, and 1 oxygen came from methanol. If one oxygen came from methanol, how many oxygens do I need to come from O2? 7, yeah. And so what's the fraction in front of O2 then? 7/2. Yeah, so that's why I leave it as a fraction, all right? And then I understand, okay, I need to multiply by 2, and then that coefficient becomes 7. So that's why I leave it as a fraction, all right? And so that's another example. All right, so that's how we approach balancing equations, combustion reactions. So just memorize that strategy, balance carbons, hydrogens, oxygens last. If there's a coefficient or a fraction in front of O2, multiply by 2 all the way across, and then you're done. All right, so that's balancing. So those ideas of naming stuff from chapter 2, it's coming back to haunt you. All right, so definitely learn those polyatomics. Hopefully you made flashcards over the weekend, right? Because it just gets it gets harder from here. All right, so, but thankfully not much memorizing here. All right, so let's get into more of the math behind chemistry and figuring out, you know, more details of what kind of reactions that we're doing in lab. And that's relating the amount of matter we have to mass. Because I don't, in the lab, when you put matter on a balance, you're just weighing things in grams. It's mass. We don't have an instrument that you can place an object on it and it tell you how many particles you have. That doesn't exist. So we need a way to relate the mass of matter that we have to how much stuff is actually there. And that's finally where we get to use the periodic table. So how we weigh out our molecules is by using their molecular weights or formula weights, and all these numbers come up from the periodic table. And so the unit of these two terms, molecular weight, formula weight, this unit is in AMU. AMU stands for atomic mass unit. That's the unit that comes from the periodic table. So like a carbon atom, its atomic mass from chapter 2 is 12.011 AMU, atomic mass units. So in order to get a molecular weight for a molecule, we just sum up all of the atoms that are there. So if we see CH4, we just take the sum of all of the atomic masses from carbon, 4 hydrogens, add them up. That is the molecular weight of CH4. Right? And so CH4 is a molecule, so it's most appropriate to call the weight of CH4 a molecular weight because it's a molecule. On the other hand is NaCl. NaCl is not a molecule because it's not a discrete molecule. I showed you the structure of it last week. NaCl is an ionic compound. It exists as a crystalline substance. So when we talk about weights of ionic compounds, it's better to call it a formula weight because NaCl is its formula unit. But the thing is that we calculate it just the same, where if we wanted the weight of NaCl, we just sum up those two masses off the periodic table. So this is just kind of clarifying terminology. If you call everything a molecular weight, no one's going to blink an eye at you, but technically NaCl has a formula weight and CH4 has a molecular weight. They're both calculated the exact same. We use the masses off the periodic table. All right, so let's actually calculate some stuff. So let's calculate the molecular weight of ethanol. And so remember, molecular weight, it's in the unit of AMU, so we just use the periodic table values. But the problem is here is I didn't give you a formula. So what do you think we have to do? Get it ourselves. But it's okay. It's okay. We're adults. We can do it. So ethanol. Eth means what? 2. So 2 carbons in a row. All right. Ethanol. So it's a alcohol. So there's going to be an OH present. So each of those carbons has, 3 additional bonds to it. One of them is an OH group. It doesn't matter where you put it. All right, so I'm just going to put it there and recognize that the rest of those bonds are going to be hydrogen atoms. All right, so if we get the full chemical formula of this substance, it's going to be CH3, CH2, OH. Or you can condense it. It doesn't really matter. C7, or no, not C7, C2H6, something like that. So you'll see that they're the exact same, all right? And so now that we have the formula, we did the hard part. Now we just have to sum up those masses. So I take inventory. I recognize, okay, there's 2 carbon atoms, there's 6 hydrogen atoms, and then there's 1 oxygen. And so let's get those respective masses off of the periodic table. So there's 2 carbons, so 2 times 12.01 AMU. And we're going to add 6 hydrogen, so 6 times 1.008 AMU. And then we're going to add 1 oxygen atom, so just plus 16.00 AMU. And then add all those up. All right? So all of this is addition. Even though there's like, some multiplication present, but all of this is addition. So how many sig figs is this answer going to go out to? If it's addition. Okay. Not necessary, yeah, so I'm glad that no one said like the number of sig figs. Instead, we're looking at not sig figs, but the number of decimal places. So our answer is going to go out to 2 decimal places. Yeah, because it looks like we're limited by oxygen and carbon. All right, so that's how we do sig figs here. It's addition rules. So the answer is something like 46.07 AMU. Okay. Okay, so one ethanol molecule will weigh about 46 atomic mass units. Okay, next one. So molecular weight, we did a molecule, so let's do an ionic compound. So we're calculating the formula weight, all right, but we calculate it the exact same. But here, again, we need to get the formula from the name. So calcium hydroxide. All right, that's chapter 2 stuff. That homework was due yesterday. So calcium hydroxide follows what naming rules? Ionic. It's an ionic compound, so we need to figure out what the formula is for calcium hydroxide. So this is ionic. So that first substance is a cation. Hydroxide is an anion. So let's recall what those charges are. So calcium in an ionic compound is what charge? 2+. That came from the periodic table. What is hydroxide? OH-. So OH- hydroxide, that is one of the polyatomics you just have to memorize, right? And so we identified the cation and anion so we can combine them so they're charge neutral. So this substance, its full chemical formula unit is calcium with 2 hydroxides present, right? So that's the hard part, getting the formula. So now let's get that weight. So again, take inventory of your atoms. There's 1 calcium atom. How many oxygen atoms are there? 2, and then hydrogen, also 2, because that 2 subscript goes to both. You can think, oh, there's 2 hydroxide polyatomics present, so there's 2 of each there. All right, and then we just add stuff up. So calcium is, I didn't write it down, is 40.08 AMU. Oxygen is 16, but I have 2 of them, so 2 times 16. And then 2 hydrogens is 2 times 1.008. Okay, so how many sig figs will my answer have? 2 decimal places, yes, because we're limited by calcium and oxygen. So you add that up. Did I write it down for myself? Yeah, it's if I add the whole thing up, it's like, oh, it's in the corner. I'm so dumb. 74.10 AMU. Perfect. There we go. Okay, so the hard part in these questions probably wasn't the adding up the masses off the periodic table, but it was actually getting from the name the chemical formula. All right, so again, chapter 2 stuff, it's important. Okay, so what else can we do with molecular weights? All right, so we see here that, okay, so from calcium hydroxide, that whole formula unit, it weighs 74 AMU. Where's most of that mass coming from? Which atom? Calcium, yeah, it's the heaviest. So oftentimes how we talk about composition of substances, we look at composition, percent composition of substances. So I can, calculate what percentage of this mass, this total calcium hydroxide mass, is coming from the actual calcium atom. And so how I can do that is just divide, take 40.08, divide it by the total mass of the substance, multiply by 100. So I can calculate the percent contribution of each of those atoms to that full chemical formula. And this will be important coming up here. So we can calculate the percent composition of each element present in 1 unit of that compound. So here's an example for methane. Methane contains carbons and hydrogens. There are those atomic masses. I get the full molecular weight of that compound is about 16 AMU. The reason that there's a 2 subscript in the corner here is I'm just trying to tell you, I'm trying not to round prematurely. I'm trying to tell you, oh, the last significant digit is the second decimal place, but I want to keep that 2 there to in further calculations. But I'm trying to tell you that, hey, this number only has 2 decimal places. All right, so this is the weight of the full molecule. So to get percent carbon of this molecule, I just take, okay, what's the total weight of just the carbon atoms and divide by the total mass. And then I can do the same thing for hydrogen. What is the weight of that, all of the hydrogen atoms? So 4 times 1.008, divide by the full mass of that molecule, and then I get 2 percentages. So what's special about these 2 percentages? What's special about those 2? If you add them up, you should get 100%. Very good, because this molecule only has carbons, only has hydrogens. So if I get the percent composition of both of those, then both those numbers will add up to 100%. All right, so, okay, let's do another example. Rust is Fe2O3. Let's name this compound. What is it? So first, remember, chapter 2 review, is this ionic or molecular? Ionic. How do you know it's ionic? Iron. Iron is a metal. Metals typically are cations. So what is this? Iron. It's iron something oxide. Yeah, why did I leave a space between iron and oxide? It's a transition metal, so you have to tell the reader exactly what the charge is of iron. So what is the charge on iron? 3+, or yes, 3+, so we put a Roman numeral 3. To remind us how to do this, recognize that there's 3 oxygens there. Oxygen, when it's in an ionic compound as oxide, is always O2-, but there's 3 of them. So the total negative charge is -6 from the anion. So that means the cations has to be +6. So since there's 2 iron atoms, each one, we cut it in half, so we see, oh, each iron is actually iron 3+. So that's how we got iron 3 oxide. Okay, so let's get the formula weight of iron 3 oxide. So we take that formula that was given and we just add up those atoms. So there's 2 irons, 3 oxygens. And so remember, we can always use the periodic table for these masses. You never have to memorize them. You're always given a periodic table, just without those element names. But I promise you, by the end of this chapter, you will memorize carbon, oxygen, and hydrogen. I promise you will. Okay, even though you don't have to memorize it. Okay, so iron is one like that I don't have memorized, so I actually have to look it up. So there's 2 irons, and it's 55.85 AMU, 3 oxygens. Does anyone know oxygen? 16, yeah, 16.00. This is one of the few that's actually 0.00. If you find a periodic table with more sig figs in it, you'll see it's actually 15.9998 or something like that. But again, you're always given a periodic table. All right, and we add those 2 up, and we get a number like 159.70 AMU, 2 decimal places. All right, so that's this is the weight of the full molecule. We've done tons of these now, just formula, add up the masses. Okay, so let's get what is the total mass of just iron in this compound, or the percent composition of iron. So to get percent iron, we just take that mass of iron and just from the iron atoms and divide by that total mass that we just got. So in this question, it'll be the mass of the iron in this sample. So remember, there's 2 iron atoms. So it's 2 times 55.85 divided by that 159.70 number we just got. And so the mass of just the iron atoms is 111 AMU. We divide by the total mass, so I'm just working this out. And then times 100 to make it a percentage. And we see that the answer is in the corner over here. So 69.944% iron. This should have 5 sig figs because all these numbers we're working with have 5 sig figs. Because now we're doing multiplication. All right. Okay. So that's how we do percent composition. How would we get the easy way? What would be the easy way to get percent composition of oxygen in the sample? Subtract it from 100. But you can test it out yourself to get percent composition of oxygen. We just take this 3 times 16 number and then divide by the total mass, and we should get, 30 something percent, whatever's left over from 100, because those two numbers have to add up to 100. Okay. All right, so great. So there's percent mass. So now, okay, so here where we got the formula weight of iron oxide, I told you, or we calculated, it was 159 AMU atomic mass units. Do you know, like, in your mind, do you know how much an AMU weighs? Is that something you can, like, yeah, I don't know. I know it's real small, right? It's the mass of an atom, so it's a really, really, really small number, okay? Is there anything in lab that can weigh stuff in the unit of atomic mass unit? No, when you think about things that you weigh in lab, what's the unit you typically see? Grams, yes. So now this is where I introduce the concept of a mole. In this class, a mole is just a counting number. It's the way that scientists go from the atomic realm to the realm of things we can actually measure. Right? So when we talk about like the atomic mass unit here, or the formula weight of iron oxide, or the formula or molecular weight of methane, we're talking about the weight of one single molecule, right? Just, that many atoms in that chemical formula. But the thing is we're never going to work with just a single, methane molecule. We're always working with a ton of methane molecules in a sample. All right, and so in order to properly weigh things in the unit of grams, because AMU is way, way, way too small, we want to talk about substances in a unit or an amount that's actually measurable. And that's where Avogadro's number comes in. So Avogadro's number is 6.022 times 10 to the 23 particles. So instead of counting individual particles or molecules in our sample, we're going to be talking about a mole's worth of these samples. It's just like saying, do you go to the grocery store and buy one single egg? No, you buy eggs in what increment? A dozen. Yeah, so it's that same idea. Instead of, working with substances on singular molecule levels, we're working in mole amounts. And I'll show you the significance here in a little bit. So mole, all right, so that's the full way to spell it, M-O-L-E, just like the animal or mole man, or this is the mole guy from The Incredibles. Yeah, and I just saw Incredibles 2, and it was really good. It was like a blast in the past. Okay, so, but oftentimes we'll see that mole is abbreviated without the L, so we'll just write M-O-L oftentimes. It's an abbreviation, all right? And so the significance of the mole is, when we looked at this balanced chemical formula, we were able to say, okay, 2 hydrogen molecules combined with 1 oxygen molecule gave us 2 water molecules. So we can also talk about this reaction in terms of moles as well, because it's just a counting number. Would it make sense if I said 2 dozen hydrogen molecules combined with 1 dozen oxygen molecules to give us 2 dozen water molecules? Would that still make sense too? Yeah, because we're working just in increments of a dozen. So instead, in this new amount that we're learning about a mole's worth, instead of individual molecules, we can say 2 moles of hydrogen combined with 1 mole of oxygen to give us 2 moles of water in that case. So it's just a counting number. All right, so why do scientists use a mole? Again, it's to get amounts and weights of stuff into a gram unit because we can actually weigh stuff in grams. We can't weigh stuff in AMU. So the great thing about the mole is that we can still use the same periodic table. So here's an example. All right, so we just did in our previous slides that a single carbon atom weighs how much? 12.01 AMU, atomic mass units, but I have no idea how much that weighs. I can't visualize how much that is. So instead of talking about a single carbon atom, I can actually talk about a mole's worth of carbon atoms. So 6.022 times 10 to the 23 carbon atoms weighs that same number, 12.011 grams instead, all right? Can you visualize like how much 12 grams weighs? Easier than 12 AMU, right? And so that's the significance of a mole, is that when we talk about a single atom, we can use the periodic table in the unit of AMU. When we talk about a mole's worth of stuff, it's the same value, but in the unit of grams. Because scientists are lazy. We don't want two different periodic tables. We want to use the same one. And so it works for single atoms. It also works for full molecules. So if we calculated the molecular weight of water, so H2O, you know, we add up the hydrogens, add up the oxygens, we would get something like 18 AMU. But the weight of a mole's worth of water, all right, so 6.022 times 10 to the 23 water molecules actually weighs 18 grams. So it's the same number, just a different unit. And that's really the power of our periodic table. It works on the atomic level in AMU, but it also works in the gram scheme of things when we're working with moles worth of substances. You're going to be more likely using grams per mole much more often with the periodic table. And again, because that's how we weigh and measure stuff in lab. Okay, so let's do a practice problem using molar mass. Definitely memorize that molar mass is in the unit of grams per mole. I don't think it's an equation, all right, the equation for molar mass. It comes from the unit itself. If we know a gram amount of our substance, we know the mole amount, we can get its molar mass. So let's look at this example. If this sample of cholesterol has this mass, what is its molar mass in the unit of grams per mole? All right, also the small detail here, we went from using the periodic table and calculating molecular weights using atomic masses. So when we talk about moles worth of things, it's actually molar mass. But again, they're all calculated the exact same way, it's just the unit's a little bit different. So in this example, we want molar mass of cholesterol. So if I get the gram amount, if I get the mole amount, I can get molar mass. So if we look at what's given, we're given moles, we're given grams. So it looks like we're given everything. So it's just plug and chug, all right? So molar mass of this cholesterol sample is something like 0.406 grams. That was given. And we have 0.00105 moles of sample. And so we see this answer should have 3 sig figs because it's all division, something like 387 grams per mole. All right, so if I had a mole's worth of cholesterol, it would weigh 387 grams. So that's what that means, okay? So let's be clever with our units. So this is the molar mass we just calculated. Molar mass, it's in the unit of grams per mole. So what is the molecular weight of just one cholesterol molecule? Can we just be clever with units here? What is it? It's also 387, but the unit now is AMU. Yes. So we can recognize that, you know, the periodic table, same numbers, whether we're working with single atoms or single molecules, or working in moles amounts of things. So we see here that, yes, in the corner, the answer is 387 AMU, but I want to prove it to you that these two numbers are the same. So if I have a mole's worth of this sample, it weighs 387 grams. So I'm going to just show you the strength of dimensional analysis. All right, so I'm going to rewrite this number in as a fraction. So if I have 1 mole of cholesterol, of cholesterol. There we go. Okay, 1 mole, it weighs 387 grams. So I actually want to change this unit, and this is kind of, I don't know, a refresher of a dimensional analysis from chapter 1. My strategy here is I want to convert the unit grams per mole into AMU per molecule. That's my strategy. All right, so what's this, you know, when we converted units like velocity, speed, you know, from like meters per second to miles per hour, the strategy was you change each unit on the top and the bottom, but we do it one at a time. So let's do that here. Let's convert grams to AMU and let's convert moles to molecules. And I gave you the conversion factors we need on the bottom here. So which one do you want to do first? Do you want to convert grams or do you want to convert moles? Grams, okay, we always start from the top and the bottom. So it looks like to convert grams to AMU, I'm going to use that first conversion factor. So where am I going to put the 1 AMU in this fraction? On the top, yeah. So 1 AMU goes on the top because then I put grams on the bottom. So I'm going to put 1.66054 times 10 to the negative 24 grams on the bottom. All right, if I cancel out those units, grams cancels. Now I'm in the unit of AMU. So I'm done with the top. So let's convert moles to molecules. So 1 mole of anything is 6.022 times 10 to the 23 particles. So I'm going to put 1 mole of anything on top is 6.022 times 10 to the 23. In this case, since we're talking about cholesterol molecules, this will be molecules on the bottom, right? And so we see those units cancel, mole cancels, and now we are left with the units AMU per molecule. Okay, so if you have your calculator out, put this in your calculator and see what answer you get. So this is how I'll put in my calculator. 387 divided by 1.6605 times 10 to the negative 24. So times 10, I'll just use the E button. So E, negative 24. And then it looks like I am dividing by that big number. So 6.02 to E, 23. And then putting that into your calculator, you will see you get the same exact, do you get the same number? Yes, you do. Yeah. So there's just a little proof and testing out our dimensional analysis that these values, changing grams to AMU, moles to molecules, we use the exact same numbers, right? So if you want to, tell me the molar mass and the AMU amount of a molecule, you don't have to do this work. You just need to know, oh, you use the same number, whether you're talking about a mole's worth of something or a single molecule. We just use different units. Okay. It's the same number, just different units. So let's try this out. Let's calculate the molecular weight of 2-propanol. Yeah, I'm really testing you here because I didn't give you the formula, so how are we going to get it? The structure, yeah, because I don't want you to memorize it. Do you want to memorize it? Nah, so just draw it. So 2-propanol is an alcohol, but what's the significance of that 2? It's where that OH goes. So what you do need to memorize is what prop means. Means 3, yep. So we need 3 carbons in a row, all right? It's an alcohol, and it's trying to tell you that the OH group is on that middle carbon. But since we're just getting, we just need to figure out what the formula is. It really doesn't matter where you put the OH group because the formula will still be the same. But, I'm just testing you. And so the rest of those bonds are going to be hydrogen. So H, 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 H. And just like when we were balancing stuff, all we're doing is trying to get that formula. So this is 3 carbons. What's the total number of hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 hydrogens and then an oxygen, right? I just need to figure out the atoms there so I can calculate the weight of it. So 3 carbons, 8 hydrogens, and 1 oxygen. So let's add up those atomic masses. Oh, this is molecular weight. So we are calculating the single propanol molecule's weight. So this has a unit of AMU, molecular weight. So, and see, I give you atomic masses here. So 3 times 12.01. So we've done this before. 8 times 1.008. And then 1 oxygen, this is plus 16. All right, so add those up and you get something like 60.09 AMU. All right, off of the periodic table. The reason we use AMU is because we're doing molecular weight. So it's the weight of just one molecule. So if we want to calculate the molar mass, we need the mass of a mole's worth of propanol molecules. All right, so a lot of them. So do I have to do all those calculations again? Nope, we just have to be super clever and recognize, okay, yep, AMU is the mass of one molecule. What's the mass of a mole's worth of propanol? It is 60.09 grams per mole, all right? So we don't have to do all those conversions, okay? Same periodic table, just different, different unit here. All right, so in chapter 1, I told you that there's like a special way we can get conversion factors from units that have fractions in it. So looky here, 60.09 grams per mole. This means if I have a mole's worth of propanol molecules, how much does it weigh? 60 grams, 60.09 grams. So the unit of molar mass is a conversion factor. It's a derived unit. So we can use it as an equality for dimensional analysis to convert from grams or moles, depending on what information we're given and what we want to calculate. So this, using molar mass, calculating it off the periodic table, but using it as a conversion factor is a very, very important skill to have for all of chemistry, actually really all of sciences here when you're working with matter. So let's look at a substance, caffeine, my favorite. Caffeine has this formula, okay? Okay, 8 carbons, 10 hydrogens, etc. And I tell you that the molecular weight of one caffeine molecule is 194 AMU. So what is the molar mass of caffeine? Do we have to calculate it? Do we have to pull out our periodic table? No, because I give you molecular weight. You can say, oh, the molar mass is the same number, so 194.19, but what's the unit of molar mass? Grams per mole. Okay, so this is the value that's going to be important to me, right? Grams per mole. So I can rewrite this as an equality that will be useful for us for dimensional analysis. So remember how we do that? We just take the number and the top unit and we set it equal to the bottom unit, but with an implied 1. So what molar mass means is that if I have a sample of caffeine, 194.19 grams of caffeine is equal to 1 mole worth of caffeine. So that's what molar mass means when rewriting that derived unit into an equality, right? 194 grams equals 1 mole. So let's pull out our chapter 1 skills and dimensional analysis and canceling out units to answer some of these questions, because it'll, again, we don't have to memorize, do I have to divide or multiply by molar mass? If you just look at the units, you'll know exactly what you need to do. So in this next question, I'm asking you, okay, how many moles of caffeine are present in this gram sample of caffeine? So we are given a gram amount and we want to calculate how many moles we have. So I'm going to start with the piece of information that's given, all right, the 0.095 grams of caffeine. And now I'm going to use that equality that we just got. So where am I going to put the 194 grams? On the bottom, yep, to cancel it out. So it seems like I'm dividing by molar mass, but again, this is not something you memorize. As long as you're just clever with your units and dimensional analysis, you'll recognize how to cancel those units. All right, so in this example, we are dividing by grams, okay, and then we get an answer like, small amount. 4.9 times 10 to the negative 4 moles of caffeine. 2 sig figs because the gram amount given has 2 sig figs, and all of this is multiplication. All right. Okay, so similar question. How much does a 0.18 mole sample of caffeine weigh in grams? So we are given a mole amount and we want to calculate a gram amount. So I'm going to start my dimensional analysis with what's given here. And I'm still going to use this gram caffeine conversion that we got before. But this time, where am I going to put the 194? This time on the top, because I want to put 1 mole on the bottom. So moles cancels, and then 194 goes up top. All right, so yes, it does seem like we're multiplying by molar mass in this case to get those units to cancel. This answer is something like 35 grams of caffeine. 2 sig figs, because the mole number has 2 sig figs, all multiplication. Okay, let's keep going. Okay, so if we kind of, I have like a way for us to navigate how we can convert from grams or mass amounts that we can actually measure in lab. We can convert to moles. That's what we did in the previous example. Now we can actually convert to individual molecules or particles of our sample, depending on what it is, using Avogadro's number. So Avogadro's number also is a conversion factor. All right, where 1 mole of a substance is equal to, it's just a counting number. So it's 6.022 times 10 to the 23 particles of that thing. So in this example, we don't want to just stop at going from grams to moles. We want to go one step further and actually know how many individual particles are there. So that's where we're going to use Avogadro's number now. But we still need to have the conversion factor in our back pocket here using molar mass. We still need this value that we got used before. In our dimensional analysis, we're just adding the idea of Avogadro's number now. So again, just keep canceling units. So we're given, we have about 7 grams of sample, so a gram amount, and we want to go to individual molecules. In order to get to molecules, we need to do a pit stop at moles first, because that's what Avogadro's number contains. It's 1 mole is a lot of particles. So we're still trying to cancel out units. So I'm starting in grams, so I want to use molar mass first. So in this example, I'm going to put the 194 on the bottom. So grams cancel, so 194.19 grams goes on the bottom. 1 mole goes up top. This is moles of caffeine. But I'm not done. I didn't ask for moles of caffeine. I asked for molecules of caffeine. So we're going to take one step further and now use Avogadro's number. So this is the equality for Avogadro's number. So where am I going to put that big number, 6.022? On the top or the bottom here? Again, just cancel units. But right now we're in the unit of moles. So 6.02 is going to go on the top. Yep, so 1 mole goes on the bottom. 6.0, so in this case, for every 1 mole of caffeine we have, there is 6.022 times 10 to the 23 caffeine molecules present. Molecules. All right. So we went from grams to moles to molecules. So if we look at this kind of guide, we went from grams to moles to molecules. In this case, we used Avogadro's number second. All right, put that in your calculator. You get that a 7-gram sample of caffeine. It has a ton of molecules. It's 2.16 times 10 to the 22 caffeine molecules are present. Okay. All right, so this next one, how many carbon atoms are present in a 6.95 gram sample of caffeine? Okay, so we just calculated how many molecules are present in that sample. For every molecule of caffeine, how many carbon atoms are there? 8. How'd you get that? The chemical formula. Yeah, it'd be like if I said, oh, if you have, I have 3 cars. 3 cars. How many tires do I have? 12, yeah, because what do you know about cars? 1 car equals 4 tires. So if I have 3 cars, then there's 12 tires. So the same idea here. You know exactly how many molecules you have, okay? And from the chemical formula, you know each molecule has 8 carbon atoms. So we just have to build this new equality that for every 1 caffeine molecule, there are 8 carbon atoms. So we are actually going to use the exact same dimensional analysis as the previous question. We're just going to add this one additional step to go from molecules to caffeine, but I'll write the whole thing out again. Right? So if I start with a gram amount of caffeine, I'm going to use molar mass and put it on the bottom. So 194.19 grams is 1 mole of caffeine. All right, and for every mole of caffeine, I have 6.022 times 10 to the 23 molecules. And for every 1 caffeine molecule, I have 8 carbon atoms. So I'm essentially just taking the last answer and multiplying by 8, because you know how many cars you have, all right, and you know that 1 car is 4 tires. If I tell you how many cars I have, you just multiply by 4. So in this case, we're multiplying by 8 because the chemical formula says there's 8 carbon atoms. And so that answer is just times 8, what is it, 1.72 times 10 to the 23 carbon atoms. All right. Okay, so we went to a gram amount, to a mole amount, to molecules, to atoms. Now this is the very last one, and it's the hardest one, but it's actually this one we just did, but in reverse. So in this example, I'm telling you how many hydrogen atoms I have. So I have a caffeine sample that has this many hydrogen atoms. What is the total mass of this caffeine sample in grams? So we actually have all of the conversion factors we need to do this question. We just need to make sure we do it in the right order. Okay, so in this example, I'm telling you how many tires I have. And I want you to tell me how many cars, or what's the mass of cars that I have. So if I have, 20 tires, how many cars do I have? 5, yeah, because you know that there are 4 tires for every car. So in this example, I'm giving you tires, and you need to spit back to me how many cars I have. So if I tell you I have 8 hydrogen atoms, I can get to molecules. So for every 1 molecule of caffeine, how many hydrogen atoms are there? In this example, it's 10, yeah, because you just look at the formula, 10 hydrogen atoms. So where am I going to put the 10 in this fraction? On the bottom, yep. So now I put 10 hydrogen atoms on the bottom to cancel it, 1 molecule of caffeine. So now I've told you the number of tires, you tell me how many cars I have. So we just did the exact same thing. All right, I gave you the number of hydrogen atoms. Now we can scale up to figure out, okay, how much caffeine do I actually have? All right, so that's molecules of caffeine. Now we can convert to moles of caffeine using Avogadro's number. So 6.022 goes on the bottom now. All right, so this is molecules, gives me 1 mole of caffeine. And since I want to figure out how many grams of sample I have, this is where I use molar mass. We've already used it like a bunch of times, but this time, where does the gram amount go? 194. It's gonna go on the top, 194 point whatever on top, and then 1 mole on the bottom. And so we see that this sample will weigh, when you put this in your calculator, 138 grams. All right, okay. So this question is actually exactly the same as the previous one we just did, just backwards. So I feel like a lot of students, like if I give you this question, most students can get this one. But when I present it this way, in the opposite direction, a lot of students get a little confused, even though it's just the same work but backwards. This is the mistake I see a lot of students do, where I give them hydrogen atoms. They recognize, oh, I need to convert that to moles and then use molar mass, but they'll use the molar mass of hydrogen. So they'll multiply this by like 1.008 grams per mole. But if you do that, all you're doing is getting the mass of hydrogen. That's it. You're not getting the full mass of the caffeine sample. Does that make sense? So that's a common mistake I see. They'll just take this number and multiply by the 1.008 and not use the molar mass of caffeine. Right, so that's the common mistake I see. Okay, so that's navigating and using this new conversion factor, molar mass, and Avogadro's number. All right, so definitely practice using those. All right, okay, so we will bring back the topic of empirical formula. So remember, I told you that this was going to be important. So this is where it's important now that we have the idea of molar mass under our belt. So we'll talk about empirical formula and bring back the idea of percent mass that we just talked about like 20 minutes ago. All right, so let's just review a little bit about empirical formulas. So if I give you a chemical formula, you can figure out the empirical formula by looking at those subscripts. All right, so let's look at these examples we looked at before. So here are my molecular formulas. What's the empirical formula of hydrazine? NH2. What's that multiplier you used? 2. Okay. Benzene. CH. Acetylene. Oh, wait, sorry, multiplier 6. Acetylene. CH also, interesting, times 2, and the multiplier is 2. And then water is just H2O. The multiplier is 1, and that's okay. Okay. So in this example, the molecular formula and the empirical formula are the same. That's fine. Okay, so the reason empirical formulas were important before, when we talked about in chapter 2, is because if I give you a percent composition of a substance, all right, and I tell you what atoms are, or what elements are present, you can actually calculate the empirical formula of any substance. Okay, but here's the thing, if I give you percent composition, you can only calculate empirical formula. That's it. Okay, so that's what I have up here. When I give you percent composition, you can only calculate empirical formulas. That's why we call it empirical, because empirical means by experiment. So the only way we can get a molecular formula of a substance, if we want a molecular formula, and we'll look at this a little bit later, is if you know the empirical formula and you know the multiplier. Right? That's how we can get the molecular formula for something. And in order to figure out that multiplier, we actually need the full like molar mass of the compound. That's the only way we can do it. Okay? And so we'll look at examples. All right. So these are my bulletproof steps on determining an empirical formula for a substance. Okay? So given percent composition. So I can tell you, like, remember we calculated the percent composition of iron and oxygen in rust, iron oxide? So if I gave you those numbers, if I said, oh, your sample is 69% iron, 31% oxygen, what's the empirical formula? You can figure it out, right, using these steps, where if I give you percentages, we need to convert those percentages in grams. And the easiest way to do that is just assume you have 100 grams of sample. So here's an example in the corner. I'll make it red so you can see it, right? So here's an example. If I have a sample that's 61% carbon and 39% hydrogen, assume you have a 100-gram sample. So how many grams of carbon do I have? 61 grams. And then how many grams of hydrogen do I have? 39 grams, that's it, all right? So if you assume 100 grams, then those percentages just become masses, because once we have masses, then we can work with those to get them into moles. Okay, so once you have grams amounts of all of your elements, we want to convert those gram amounts to moles of each element. How do we do that? Periodic table, use the molar mass for each of those respective elements, okay? So turn grams of each element to moles of each element. So once we have moles of each element, you're going to see like fractions, like really small numbers. They're not going to be whole numbers. So what we want to do is identify that smallest mole amount from step 2, and you're going to divide all those mole amounts by the smallest number. And the reason we do this is to ensure that we have a whole number integer. I know there's a lot of information on this slide, so just write it down, and then we will just do an example, and it'll all make sense. Okay? So once you do step 3, then we get our mole ratio, and it might require some rounding. Okay, so don't see a lot more people writing stuff down, so let's just do the example, walk through the bulletproof steps on how to do it, and hopefully it'll make more sense. Okay, so here I have a compound. It has 3 elements present by mass. So here's your strategy. All right, so it's the same slide, but just all condensed here. All right, so we have carbon, hydrogen, and oxygen. Let's get the empirical formula. So I give you percentages. So my first step is to get all of these elements in grams. So how do I do that? Just assume we have 100 grams of sample. So if I have 100 grams of sample, how much carbon do I have? 68.54 grams of carbon. I don't like red. Let's do blue. How many grams of hydrogen do I have? 8.63 grams of hydrogen. And then I have 22.83 grams of oxygen. So again, I'm just assuming we have 100 grams of sample. Those percents by mass just become gram amounts. It actually doesn't matter what number, how much sample you start with, as long as those percentages work out. 100 is just an easy number. Okay, so we went from percent elements to now grams of elements. So now we want to get to moles of elements. This is where we're going to use molar mass for each of those respective elements. So how do I get to the molar mass, or sorry, how do I get to the mole amount of carbon if I know the gram amount? So yeah, we're going to divide by 12.01 in this case. So 12.01 grams of carbon is 1 mole of carbon. Then we do the same thing for hydrogen, but we want to use the molar mass of hydrogen. So for every 1.008 grams of hydrogen, there's 1 mole of hydrogen. 1.008 came from the periodic table. Okay, if oxygen is, the molar mass is 16 grams per mole, where's the 16 going to go? On the bottom. So 16.00 grams of oxygen is 1 mole of oxygen. Right? Okay, so putting that all together, so I just did all the writing the math out, so I'll just take out my calculator once to do all these calculations. So in this sample, I have 5.707 moles of carbon, 8.561 moles of hydrogen, and then 1.427 moles of oxygen. Okay. Sig figs don't really matter here because we're just trying to get integer numbers. Okay, have you ever seen a chemical formula that looks like this? C 5.707, H 8.56, O 1.42, no. Is that a chemical formula? No. So we need to figure out what the ratio, the whole number ratio is between atoms. So how we do it to force these numbers into whole numbers is we identify the smallest number. What's the smallest number of the 3 we just got? 1.42, whatever. So what we're going to do is we're going to divide all of those numbers, all 3 of these numbers, by 1.427. 1.427. 1.427. Because when we divide a number by itself, we always get the number. When we divide a number by itself, we always get 1. So when we do this, we ensure that one of the mole ratio numbers is a whole number. So when we divide oxygen by itself, we get that, oh, for every 1 mole of oxygen we have, there are, so when you get this, when you do hydrogen, you get something like 6.002 moles of hydrogen and 3.99 moles of carbon. Now we're getting closer to something that looks like a mole ratio. So 3.99 is really, really close to what number? 4. 4 moles of carbon, and then 6.002 is really close to 6 hydrogens, and then one oxygen. So there is our mole ratio, all right? So our full chemical formula there is in the corner. So C4H6O. So in these examples, like how we rounded, so 3.99 very obviously rounds to 4. 6.002 obviously rounds down to 6. We have to be really careful with our rounding though, because sometimes we don't round, all right? There's other ways to do it. So here, if step 3 isn't a integer, multiply all mole values by a factor so that mole ratio is an integer. So for example, if you do all the calculations and you get a number like 1.96, what do you think that would round to? 2. Yes, that rounds to 2 moles. So yeah, go ahead and round 1.96 to 2. But what about 2.501? Is that going to round to 3? No, we don't want to do that. Okay, we don't want to do that. So instead, we're actually going to multiply all those ratios we just got by 2, because when we multiply by 2, we get really, really close to what integer value? 5. Yes, so 5 moles. So don't round 2.5 to 3. Okay, we're not close enough to a whole number. We actually want to multiply by an integer. What about 2.33? Does that round down? No. What do you think we'll do to make that an integer? Multiply by 3. But again, you multiply everything by 3 if we do that. And the next example, we do this. So 2.33 times 3, I think, is 7. Yeah, okay. Okay, so let's do an example where it doesn't round. Okay, so here's another example. We have phosphorus and oxygen. What's the empirical formula? So in this example, I give you gram amounts. So do I have to assume I have 100 grams of sample, convert percentages to grams? No, you can just start with these numbers. You don't have to do the percents to grams in this example. So I'm just going to start with 4.37 grams of phosphorus, 5.63 grams of oxygen. All right, and convert those to moles of each of those elements. So the molar mass of phosphorus, 30.97 grams is 1 mole of phosphorus. 16.00 grams of oxygen is 1 mole of oxygen. Right? So mole amounts, there is 0.1411 moles of phosphorus and 0.3518 moles of oxygen. So does that mean my formula for this compound is phosphorus 0.1411, 0.3518. Is that something you've ever seen? No. So how we turn those numbers into whole numbers is to identify the smallest number we just calculated. So in this case, it's phosphorus, and we divide both those numbers by that smallest number, because that ensures us that one of those numbers will be a whole number. All right, so we have, 1 mole of phosphorus present, and then when you do that division, what do we get? For oxygen, 2.5 moles of oxygen. Okay, so does that mean my answer, my empirical formula, so that one's not right, does that mean that this formula is P102.5? No. Oh, so how about I just round 2.5 to 3? So it's P03, is that right? No. So what we want to do instead is to get rid of that 2.5, recognize 0.5 is a fraction, right? It's like, a half is 1 over 2. So what I'm going to do instead is multiply all of these by 2. So then I get, for every 2 phosphoruses, I have 5 oxygens. And that's how I maintain that mole ratio. Right? So my full chemical formula here is, P2O5. All right? So sometimes we have to do that when our empirical formula doesn't have like a single element. All right? And so sometimes we see these fractions that we have to work out ourselves. All right? So do not round. Do not round 2.5. Don't round 2.33. Okay? We need to multiply by some integer to get that whole number ratio, to get our empirical formula. Okay. Okay, 7 minutes. All right. So all of these that we've just done have all been empirical formulas, the simplest ratio. So how do we get a molecular formula? So in order to figure out the full molecular formula for a compound, we need 2 things. First, we need the empirical formula. And the second thing we need to know is the full mass of the molecule. If we know those two things, we can get the full molecular formula. We could go from, benzene is C6H6, but if we did percent composition, we would only be able to get CH, that empirical formula. To figure out that the compound I'm working with is C6H6 is I need to get the multiplier by comparing the mass of the full molecule to the mass of the empirical formula. All right, I think it's better if we just do an example. Okay, so we did one of the examples where we got the empirical formula is C4H6O. But I tell you that the molecular weight, the full weight of this molecule is 140 grams per mole. All right, what's the molecular formula? It's kind of like guess and check. Okay, so I know the weight of the full molecule. I know the empirical formula. I know the empirical formula, or the molecular formula, will be some whole number integer, right? Because the multipliers are always whole numbers. So I just need to figure out how many empirical formulas fit inside that molar mass. So I'm trying to figure out my molecular formula. But I know that my molecule weighs 140 grams per mole. So let's calculate how much does my empirical formula weigh? And we can just be really like eyeball-y here because we're just trying to figure out how to scale it. We're not like calculating perfect mole amounts here. So I recognize there's 4 carbon atoms, so 12 times 4. There's 6 hydrogen atoms, so we're gonna add 6 grams, and then add an oxygen atom, so 16. So I think that adds up to, okay, that empirical formula weighs 70 grams per mole, about. All right, just one empirical formula. The whole molecule is some whole number, like multiple of that. So what's the can you tell what the multiplier is in this example? Yeah, it's 2. So if that's how we get the multiplier. All right, so can you tell me what the molecular formula is? It's going to be C8H12O2. So essentially, we're just comparing the mass of the empirical formula to the molecular formula that's given, or the molar mass that's given, and we need to figure out that multiplier and work our way back up. All right, so from percent composition, you can never go to molecular formula directly. You only can get empirical. The additional piece of information you need is its molar mass, the full molecule's molar mass. Okay, so let's see if you got it. Okay, consider these two things. Benzene and acetylene. All right, so it's the C6H6 and acetylene, C2H2. True or false? Benzene and acetylene have the same molecular formula. No, false. Benzene and acetylene have the same empirical formula. True, yes. Benzene and acetylene have the same percent carbon and percent hydrogen by composition. It is true, yeah, it's true. Calculate it yourselves. Benzene and acetylene can be identified or like separated by percent composition analysis. False. Why is that false? Percent composition only determines what? Empirical, yes. Percent composition only tells us empirical. And since they have the same empirical formula, we can't tell them apart. All right. Benzene and acetylene have the same molar mass. That's false because they have different molecular formulas. They weigh differently. All right. Okay, and so fine, let's put it all together. Benzene and acetylene can be identified if we know percent composition and the molar mass. Yes, that is true. Yes. So that's the whole purpose of everything we just went through. That's why empirical formula is important. Because we can only get, if we have percent composition information, we can only get percent or empirical. We need molar mass information to go one step further. Okay, so I'll have to end here. So this will pick up here on Thursday. And hopefully finish off chapter 3 on Thursday.